Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. The new supercomputer is the quintessential human invention. It is the very symbol of genius and inspiration. Inventing a supercomputer is about turning science fiction to non-fiction. Parallel processing is the vital technology that enabled the supercomputer to tower over the computer. Practical parallel processing was a new path that led to a new computer science and a new computational physics. Back in 1989, my discovery of practical parallel processing made the news headlines because it enabled us to see computers and supercomputers in a different way, namely as parallel processing or solving a million problems at once instead of solving only one problem at a time. Parallel processing is the crown jewel inside every supercomputer that enables it to solve grand challenge mathematical problems that will otherwise be impossible to solve. It's impossible for me to have solved the grand challenge problem of supercomputing and solved it across my new internet and solved it without correctly visualizing in advance how to mathematically solve it across that new internet. In the early 1990s, I was appointed as a distinguished visitor to academia and from the Computer Society of the IEEE. The IEEE is the acronym for the Institute of Electrical and Electronics Engineers. The IEEE is the world's largest technical society. The IEEE Distinguished Visitor Program sponsored quote-unquote top technology leaders and innovators and sponsors them to lecture at institute chapters and at university computer science departments in the United States, Canada, and Europe. An IEEE Distinguished Lecturer serves as a role model to its members and to up-and-coming scientists and engineers. As an IEEE Distinguished Lecturer, my goal was to explain how I discovered that massively parallel processing makes computers faster and makes supercomputers fastest and will become the vital technology that will underpin every supercomputer. I asked a big question in supercomputing that had never been answered before. That overarching question was this: how do we parallel process across a new internet that is a new global network of 64 binary thousand computers? To quote myself from my lecture at the 1991 International Congress for Industrial and Applied Mathematics, I explained that, quote, my experimental discovery of massively parallel processing occurred across a new internet and occurred on a storyboard, on a blackboard, and within a motherboard. And my eureka moment of the world's fastest supercomputer and computation occurred across my new global network of 64 binary thousand motherboards. I visualize my act of parallel processing across my new internet as a play in Broadway, New York, in which the production oil field was my stage, unquote. My supercomputing quest of the 1970s in Oregon, United States, and 1980s in New Mexico, United States, was to figure out how to solve partial differential equations that were defined within the interior of an initial boundary value problem of extreme scale mathematical and computational physics. My quest was to figure out how to solve those partial differential equations that were otherwise impossible to solve. Those partial differential equations were impossible to solve on only one processor that was not a member of an ensemble of processors, but possible to solve across millions upon millions of tightly coupled and identical processors that were equal distances apart and that computed in parallel. Each processor within that ensemble of processors operated its own operating system. Each processor had its own dedicated memory. Each processor shared nothing with nearest neighboring processors. And along that line of thought, I continued my research lecture on the 9 partial differential equations that I invented and that I was presenting to research mathematicians that were attending the 1991 International Congress for Industrial and Applied Mathematics. I continued as follows. The place, the Niger Delta oil producing field in southeastern Nigeria. The holes, one production well for producing crude oil and natural gas, and 2 or 3 or 4 injection wells for injecting water into the oil field. The event, crude oil, natural gas, and injected water flowing along 3 mutually orthogonal spatial directions that were mathematically named X, Y, and Z directions. The rules, some laws of physics, including the second law of motion that was discovered 3 centuries earlier. My new equations, a system of coupled nonlinear, time-dependent, 3-dimensional, and state-of-the-art partial differential equations of modern calculus and extreme-scale computational physics. That system of equations that I formulated for petroleum reservoir simulations included the 9 partial differential equations that I invented to incorporate 36 partial derivative inertial terms, which are calculus terms that represented the inertial forces in the algebraic formula force equals mass times acceleration. My never-before-seen algebra, 24 million system of linear equations of algebra that was a world record in size in the 1980s. The supercomputing lesson that I learned was that in solving the grand challenge problem, there is a Grand Canyon of difference between physics and mathematics and computing. Solving the grand challenge problem of supercomputing demanded that the polymath must shift from disciplinary to multidisciplinary thinking and shift it up by 2 intellectual levels. that polymath must shift up from the laws of physics that were discovered 3 centuries ago to the laws of logic that were developed 2 centuries ago to the laws of numbers that were invented within the last century.
Insightful and brilliant lecture.